Okay, so in the previous module, we had taken up friction factor for turbulent flow in a hydraulically smooth pipe. If you come to the slides, this was the universal velocity profile which we had taken, u plus equal to y plus and u plus equal to 5 log of y plus minus 3.05 and u plus equal to 2.5 log of y plus 5.5. So what did we try to do is, if you get to see this here, we took pi r squared u average equal to 0 to r 2 pi r u dr. Now in this we replaced this u and y in terms of u plus and y plus terms and substituted for u plus the universal velocity profile, did the integration, rearranged the equation, wrote that in terms of f and re, and we could get an implicit relation for f in terms of re and compared those results with the experimental results, compared the equation with experimental results, and we found that that was working very well, and that was done based on Blasius experimental results done by Prandtl. So it was a combined work of Prandtl and Blasius. So what did we do? This is the equation we took, we non-dimensionalized and we substituted for u plus and did the algebra. We got u average by u tau, wrote it as 8 by square root of 8 by f, substituted that, and we got this equation 1 by root f equal to 2 log of re root f minus 0.8. So this is what is called Prandtl's universal law of friction, and it is valid for Reynolds number up to 3.4 into 10 to the power of 6. Now Blasius also gave a relation, but the Blasius relation was very empirical, that is simple curve fitting a re to the power of b. So he got a as 0.3164, b as minus 1 by 4. So it works very well only to a limited range. So this why Prandtl's range is very high. If you come to the slides, I showed that these results were revisited in Princeton University very recently in 1998, and they just found that the equation, they extended that equation up to 35 into 10 to the power of 6 Reynolds number with an additional parameter, not an additional parameter, additional term involving Reynolds number and root f, and constant slightly they changed, and interestingly this equation predicts up to 1.4% with the experimental data. So now what I am going to do is, we will try to understand what is hydraulically smooth and hydraulically rough pipe. We will try to solve a simple problem. That is, let's take up given, let's solve this problem. I would highly encourage you, all of you, to solve, and your students also, you can encourage them to solve this problem. Diameter equal to 50 mm. I have just taken a 2-inch pipe. Length as 10 meters. Reynolds number I have taken 1 lakh, 10 to the power of 5. And viscosity of water I am taking it as 0.001 Pascal second, and density I am taking it as 1000 kg per meter cube. These are the properties. Now what is the Reynolds number? What am I trying to do is, in this problem I am trying to give the feel of y plus and laminar shear stress and turbulent shear stress. I am trying to give the feel from this problem. So Reynolds number equal to rho u average diameter by viscosity. So Reynolds number, I want to get u average, so that's why I am doing this. 10 to the power of 5 equal to density is 1000, u average, diameter is 50 mm. If I convert that into meters, into 10 to the power of minus 3 upon 0.001. So you get this u average, this and this gets cancelled out. 1 lakh upon 50,000 fetches you 2 meters per second. This is your u average. Now can I get my F? Yes, 1 by root F equal to 2 log Re root F minus 0.8. If I substitute Re and solve this by trial and error, either using trial and error method, if you use trial and error method, or Newton-Raphson method, one of the methods if you use, you can get this F as 0.018. So I am not doing the trial and error, I am leaving that as exercise for you. Kindly do that. So you get F equal to 0.018. Now what is F? F equal to 4 CF. What is CF? Tau wall upon half rho U average squared. Correct? So now F is found to be point implies 0.018 equal to 4 into tau wall upon half, rho is 1000 and U average squared is 2 squared. So you get tau wall equal to 9 Pascal. But now what is U tau? U tau equal to square root of tau wall by rho. That is equal to tau wall is 9 upon rho is 1000. So you get 0.09487 meters per second. Now what is Y plus? Y plus equal to YU tau by nu. So if I want Y plus is 5, Y I want to find, actually U tau I cannot take directly 0.09487. Why? Because this is overall friction factor, that is it is involving both laminar and turbulent, but I will just go ahead and make bold assumption that this is good enough for me. So I will take this as U tau as 0.09487 upon, remember this is just to get the feel, it is not that it is correct. Actually if it is correctly if I have to do, I have to take U tau equal to mu del U by del Y only, but I am not doing that, I am just taking directly from F whatever I get. So you get Y into nu is 0.001 upon 1000, that fetches me Y equal to 5.27 into 10 to the power of minus 5 meter. That is in mm it comes to 0.05 mm. You see, why did we do this? In spite of taking such a high value of U tau, you are getting a Y of 0.05. So what I mean here is, if my surface, geometric surface roughness, if my geometric surface roughness is less than 0.05 mm, we call this as hydraulically smooth pipe. That means the fluid doesn't feel that it is rough, it feels that it is smooth. Okay, but if the geometric surface roughness is greater than 0.05 mm, so it is called hydraulically rough pipe. Hydraulically rough pipe. So now I will assume that the velocity profile U average by U center line is equal to 2n squared divided by n plus 1 into 2n plus 1. This I will derive in the next module. Okay, actually what I have done is I have taken the velocity profile as a power law. Okay, I will do this derivation of how did I get this in the next module. For now if I take this, so Reynolds number equal to 1 lakh and n is 7, if I take, I get, and the U average I have gotten 2 already, U center line equal to 2 into 7 square divided by 7 plus 1 into 2 into 7 plus 1 if you do, you are going to get U center line equal to 2.45 meters per second. What am I trying to do is, I am trying to calculate the laminar shear stress and the turbulent shear stress. So U by U center line is equal to 1 minus of R by R to the power of 1 by N. This is my power law. This is experimentally obtained, and N is a function of Reynolds number. So if you differentiate this with respect to R, because your tau wall laminar equal to mu du by dr. So if you need du by dr, if you differentiate this du by with respect to R, and you want, let us say at a location 1.25 mm from the wall, at R equal to 1.25 mm, if you want to calculate, if you differentiate this, what do you get? U center line into 1 by N into 1 minus R by R to the power of 1 by N minus 1 into differentiation of minus R by R, that is minus 1 by R. If you substitute all the values, that is you get minus U center line upon NR into 1 minus R by R to the power of 1 by N minus 1. So 1 minus N by N, if you just do that, you get U center line we have just found as 2.45, N is 7, R is 25 mm into 1 minus 12.5 by 25 to the power of 1 minus 7 by 7, you are going to get this as 25.36. So tau is equal to, tau wall laminar equal to mu du by dr, mu is 0.001 into 25.36, you get 0.02536 pascals, which is very small. Now if you take tau wall, at the wall is 9 pascals, and the shear stress, as I had shown you, is varying linearly. So at the center shear stress is 0 and at the wall it is maximum. So you have tau wall at R equal to R by R into tau wall. So at R is 12.5 divided by 25 into tau wall is 25 pascals. You have 9 pascals, you had gotten 9 pascals, so you get 4.5 pascals. So tau turbulent divided by tau laminar, if you have to compare, tau wall minus tau wall laminar upon tau laminar, if you take, tau wall is 4.5 minus 0.02536 upon 0.02536, you get approximately 177. So what point is, the tau turbulent is so large compared to the laminar. So in the turbulent flow, that's why when we did the friction factor correlation, we took only A log y plus B, because that is the one which contributes from the turbulent boundary layer. You don't have to bother about viscous sublayer contribution because its contribution is very less. This problem is only just to give you the feel of y plus laminar shear stress and turbulent shear stress. I know very well that I have assumed the u tau directly to get the feel of y, but actually if I have to take, I have to take u tau as mu del u by del y. Okay, so this is just to get the feel of hydraulically smooth and hydraulically rough pipe. So now let us take up friction factor for turbulent flow in a hydraulically rough pipe. I cannot use the same universal velocity profile. For hydraulically rough pipe, I have to come up with the universal velocity profile. So, before I say what should be the roughness thickness or the roughness height, roughness elements are large enough to break viscous sublayer. I have already told this, but I have formally written here viscous sublayer. So that is, I define epsilon plus equal to epsilon u tau by nu. If it is less than 5, then it is hydraulically smooth. If epsilon plus equal to epsilon u tau by nu is greater than 5, it is pipe is said to be hydraulically rough. So, from experimental data, it has been found that u plus equal to 2.44 log of y by epsilon plus 8.5. How do we get this? I will explain you now. Now, let us take our general relation, universal velocity profile. What was its form? U plus equal to 1 by kappa log of y plus some constant, let us say C5, okay, for y plus greater than 5. Now, u, I will write this as u by u tau equal to 1 by kappa log of y u tau by nu. I have just substituted for u plus and y plus C5. When r tends to epsilon, that is at the surface, the y tends to, not r, y tends to epsilon, that is on the surface. This is my rough surface. When y tends to epsilon, my u is 0, right. So, I get 0 equal to, when y tends to epsilon, u is 0. So, u left hand side is 0, 1 by kappa log of y is epsilon u tau by nu plus C5, okay. So, you have gotten C5 now. Substituting this C5 equal to minus 1 by kappa log of epsilon u tau by nu. Substitute this in this equation. So, you get u by u tau equal to 1 by kappa log of y u tau by nu minus 1 by kappa log of epsilon u tau by nu, okay. So, now u by u tau is equal to 1 by kappa, this is log a by b. If you do a by b, u tau by nu gets cancelled out. So, you get log of y by epsilon, okay. So, but then this does not work. So, we take some constant log c also, okay. So, when you compare with the experiments, this form, so you get 1 by kappa as 2.44 and constant as 8.5. So, my u by u tau is equal to 2.44 log of y by epsilon plus 8.5 is what I am going to use for my friction factor correlation, okay. Same steps whatever we had followed for the friction factor to find in case of smooth pipes, same steps we are going to follow, okay. But only thing is that we need to appreciate that here earlier for smooth pipe friction factor was only a function of Reynolds number, but for rough pipe, remember when I say rough I mean hydraulically rough, not geometrically rough. Friction factor is a function of not just Reynolds number but epsilon by d, that is the surface roughness, okay. So, we can expect now friction factor not just Re but also epsilon in our relation. So, let us see how do we go about that? Now again, q dot equal to, I will not be able to complete this in this module, but let us do this and take it whatever we can complete. Pi r squared u average equal to 0 to r 2 pi r u dr. This I had told last time also in the derivation. Just quickly, this is my y, this is my r, this is capital R, small r equal to capital R minus y, dr equal to minus dy. When r equal to 0, y equal to capital R, and when r is r, y equal to 0. We had done this, so that is why I have gone a little fast. So pi r squared u average equal to 0 to r, because already dr will become minus dy and this becomes r to 0, I have flipped that. So 2 pi r minus y u dy. This is what we get. So now let me multiply both sides by 1 by u tau. Pi pi gets cancelled out. So you get r squared u average by u tau equal to integral of 0 to r 2 into r minus y u by u tau dy. Okay. So now this is r squared u average by u tau is equal to integral of 0 to r 2 into r minus y. What is u by u tau? U by u tau is nothing but u plus. So you have u plus dy. But what is u plus relation we have gotten? Just now I wrote u plus equal to 2.44 log of y by epsilon plus 8.5. So if I write u plus equal to a log of y by epsilon plus c, a and c we will substitute later on. So if I substitute that, I get r squared u average by u tau equal to 0 to r minus y, u plus is a log of y minus a log epsilon plus c into dy. Now let me integrate this equation. So you get r square u average by u tau is equal to 2, I have missed out here, sorry, 2 into first term a r y log y minus of a r y within the limits 0 to r minus of this one. Now y log y I have to differentiate. So I get a y squared by 2 log of y plus y squared by 4 minus y squared by 4 into a with the limits 0 to r. Okay. Next, minus of a r y log epsilon, because this is a log epsilon r, so you get y 0 to r plus a y squared by 2 log of epsilon, because you have y a log epsilon, so you get y squared by 2 0 to r, minus into minus it makes it plus, minus of plus of c r y 0 to r minus c y squared by 2 between the limits 0 to r. Okay. So I know it's a lot of bookkeeping, but we need to do it. There is no other shortcut for this. R squared u average by u tau is equal to 2 into a r squared log r minus a r squared minus a r squared by 2 log r plus a r squared by 4 minus a r squared log epsilon plus a r squared by 2 log epsilon plus c r squared minus c r squared by 2. So we are reaching r squared can be taken as common. U average upon u tau equal to 2 into a log r minus a by 2 log r plus a by 4 plus a by 2 a by 4 minus a log epsilon plus a by 2 log epsilon plus c minus c by 2. So this reduces to u average by u tau equal to 2 into a by 2, this term and this term, a by 2 log r minus 3a by 4, because this term and this term, now you have these two terms, you get minus a by 2 log of epsilon plus c by 2. So these two we can combine. So I can write this as u average by u tau equal to a log r by epsilon, I have subsumed 2 inside, minus of 3 by 2a plus c. Now it is time to substitute a equal to 2.44, c equal to 8.5, and if you recall, u average by u tau equal to u average by square root of tau wall by rho, it is equal to 1 upon square root of tau wall by rho u average square, that is nothing but 2 by cf, that is nothing but 8 by f. This we have done earlier. So this is square root of 8 by square root of f equal to 2.44 log of r by epsilon, and substituting those constants, you are going to get this as 4.84. So in this module I have gotten this far. I will have to convert this into log and convert this in terms of Reynolds number and epsilon. I will do that in the next module. So much for this module. Thank you.